Dos, tres. Hey Diego, how you doing?
Hey Cuauhtemoc, I'm doing okay. I hope you're doing also fine. How's it going?
It's going all right, thanks for asking. And today we're going to talk about the power of quantum machine learning. So this paper claims that the new generation of machine learning methods are going to be not only better at generalizing with the same amount of data, but also they're going to train faster using quantum computers and the properties of quantum computing and is order of magnitudes better at learning and also at training. I know you have worked on your masters with quantum computers, right?
Yes. I mean, I had the chance to learn the theory of quantum computing using the book of Nielsen and Schwang. Even though it's a kind of old book, I think it's the definitive textbook to learn quantum machine learning. So I think my favorite part was the quantum Fourier transform, the algorithm that allows us to have the short algorithm. I think this paper is also going to be very interesting for you since you did your PhD in machine learning, right?
Yes, I work with machine learning during my PhD. And also, let me show you the paper. So
Sure.
in machine learning, just a reminder, is kind of the brain of all of AI things like ChatGPT, self-driving cars, and so on. And in this paper, they compare how the neural network performs using classical computers and quantum computers, and also how the performance is between these two, how faster they train, how much of like the upper bounds, how well can they be. And there is something in machine learning called the error function, which is the lower the better. We want our models to be uh, as accurate as possible, and the error function tells us how far are we from having a good result. And in this paper, they used something called the average feature information matrix or the feature information matrix. And the eigenvalues of these metrics tell us how the landscape of this error function looks like, specifically the curvature. And the eigenvalues, the larger they are, it means we have more bumps, more valleys, and the closer to zero the eigenvalues are, it means this function looks kind of flat. And a flat function is harder to learn. We need to explore more the function. We need to kind of uh, see where the minimum is with a little bit of more effort than the usual. But if this function kind of has more bumps and valleys and is not as flat as a constant function, then it's going to be easier to train. It's going to be easier to find the minimum in less iteration as in as necessary. In this figure, they have three models. They have the pink one, which is the classical neural network, and as they have the blue one, the easy quantum model, is kind of a mix between a quantum and classical one, and the green one is completely quantum. They use advantage of the exotic properties of qubits, and we have seen here in the bottom figures that the size in the green one is larger than the pink one. So that means that, Diego, in the classical neural network, the eigenvalues on average are very small. So this function is going to be hard to learn. We would need some fancy algorithms to minimize it and explore a little bit more the landscape of this function. But in the quantum neural network, this is easier. Why? Because on average, the eigenvalues of the Fisher information matrix are larger. So this function is like a roller coaster. So for the algorithms of minimization, it's going to be easier to find the minimum because it's less boring, and that translate is going to be easier to learn.
Nice. Nice. So we can say that this is the first proof. I mean, if the paper poses a question, okay, it's really well worth it to work in so-called quantum neural networks. We already have a quantum advantage.
Yes, it seems at first order that quantum machine learning has some advantages over the classical machine learning we know now.
That's pretty cool. So myself, I want to pose another question about the generalization properties of the models. So a question that the paper addresses is how to quantify the generalization properties of models. So actually, so far, the quantities related to this generalization are also scaling with the number of parameters to optimize. I mean, I have here a simple model of a deep neural network. That means, I mean, in neural networks, we want to optimize the weights uh, of the neurons. So a quantity that scales with the number of neurons we want to optimize is not very, very efficient to tell us how well it's going to generalize, because actually nowadays the models can have millions or tens of millions of that order of parameters. So actually we need a quantity that can be used much more, that actually we can quantify, that cannot scale with the number of parameters to optimize. So the paper uses also the quantum information to define a quantity called the effective dimension. So basically, this effective dimension is proportional to the properties of the generalization of the model. So here in the figure 3, they present how this parameter is going to evolve with the number of data at disposal. So again, they compare the classical model in the purple line, this mixture between the classical and the quantum algorithm in blue, the easy quantum model, and finally the full quantum neural network in green. So they claim and they prove in the supplementary material that this quantity has a bound with the number of data. So actually, we already see that we are reaching that bound much faster with the quantum neural network compared with the classical algorithm. In the beginning of this, or beginning with the smaller sizes of data, and actually we can reach much faster the bound comparing with the two. So they claim that actually, yes, so the generalization properties of the quantum neural networks are much more efficient than the classical models. So, Potemo, since you tell us that the landscape in quantum neural networks are going to be steeper, that's also directly related, and the paper claims so, to the trainability of the data. So they can compare how well or how fast this loss function, error function are going to be optimized to zero with a number of iterations. So here in the figure 3b, they compare again the three models, the classical, the easy quantum model, and the full quantum neural network. And we see directly that actually for the simulation they perform, the uh, quantum neural network is going to optimize much faster comparing the other two algorithms. And actually, they have a simulation in real hardware using the IBM infrastructure to have the same kind of simulations like with real hardware, and they claim that actually in real hardware is going to be uh, much more optimized compared to the simulations, which is also a surprise actually, because they claim also, it's a fact, that the intrinsic noise of real hardware is going to also flatten the landscape of the error function. So uh, we expect that using real hardware. I mean, this is an open question that the paper claims, but it's not directly addressing how this noise is going to degrade the advantage of the quantum neural network. So it's really impressive that actually doing real hardware that they did in the paper, actually they show that indeed is going to be better, even better than the simulation they perform.
Yes, not only the quantum version of machine learning performs better with the same amount of data, also it trains faster than the classical ones. So in this way, we will see a version of ChatGPT with steroids because with the same amount of data, it can reach higher levels of generalization, which kind of tells us how smart the model is. Isn't it the case?
Yes, indeed. I mean, it's really impressive that, yeah, actually using quantum neural networks is not going to just generalize better, but actually it's using less resources. I mean, comparing classical bits with qubits. And of course, and the paper says that, okay, it's because we have these properties of the qubits that they can be correlated. I mean, we can have a correlation between the qubits. I mean, one way to perform it is through this phenomenon of entanglement. And actually, it's very impressive that they say yes. I mean, it's because we have correlation between the qubits entanglement that actually we can claim they prove it. They prove it in the paper that we have quantum advantage. It's I think it's really difficult question how directly these two properties are very related. I think it's for further research, but yeah, I mean, right now, and it's very clearly solved. I mean, if the paper posed the question, okay, is it worth it to work with quantum neural network? The answer is definitely yes. I mean, we're going to use less resources, less amount of qubits. We have the power to better generalize the models. So I think my opinion is like yes, we are ready. We are ready to jump into these problems right now.
Yeah, it's going to be a second revolution. As we know, now AI is going to be completely different when the quantum computers finally arrive. And I know you have some more experience with this, but do you think it's going to be soon, anytime?
I hope so. I mean, the real problem. Yes, I
The
mean, I think the challenge, the challenge. I think the challenge right now with quantum computing is actually in the hardware part, because yes, of course, I mean we are dealing here with quantum systems and correlations between quantum systems. So establishing the correlations between quantum systems through interaction is really difficult in the sense that we want correlations, interaction between the qubits, but we want to avoid the qubits to be correlated to the environment because that's the mechanism through we degrade the coherence properties of any quantum system. So, I mean, as far as we can scale the quantum computers, the number of qubits, I mean, right now the order should be thousands of qubits. So, as far we can scale that to millions of qubits and even further because the quantum correction error algorithms requires much bigger amount of qubits. Yes, we are going to reach those aims. So yeah, I mean, I think right now it's a problem of the hardware, how to manipulate better qubits. Of course, I mean, there is a huge amount of research right now in different platforms, superconducting qubits, neutral atoms, uh, diamond vacancies of nitrogen. So yeah, I mean, I really hope,
Interesting.
I'm
We don't even have the quantum computer yet, and we already have seen that quantum machine learning outperforms completely the classical version, and it seems like everything is done there, just waiting for the quantum computer to come, and then we're gonna have for sure a revolution on the computer science and AI as we know now. Thanks
exactly
for
right.
your time, and I hope you enjoyed this. Definitely something we should talk about. It's very interesting. Should make a YouTube video, a YouTube channel.
Sure, cool. I had a great time.
Thanks. I will see you around and
See you around,
see
Gustavo.